So this is the same diagram we just showed, but it's broken down into a little bit more detail to really demonstrate this process of encapsulation and decapsulation. So this is actually a representation of HTTP-based communication, which is what we use when we browse web pages. So this is an example of you browsing a web page, and it begins with you on the left. You're the system on the left, and you use your browser and you tell it to go to google.com. So there are some other things involved in there. There might be a DNS request or an ARP request and some other packets at play that help set this up and allow for this communication. We're going to ignore that for now and just focus on the actual HTTP request. So when you request this web page from your browser, what you're doing is requesting it from an HTTP server, which is the system on the right. So we're sending the request in the form of a packet, but first we have to build that packet. So this begins with the HTTP protocol, which is what the browser is using to formulate the request. The request is formulated, and we have essentially a block of HTTP data. Now, we can't just send the HTTP data as it is. We need all sorts of other things. We need the communication to be reliable. We need network level addressing to get it out of our network. And we need local addressing, data link addressing to get it to the right device within our network that can forward it along, which in this case would be a router. So what we have here is that HTTP data is passed down to the next really network focused layer we're concerned about, which is the transport layer. The transport layer is responsible for ensuring reliable delivery of the data, and it does that with a set of additional data fields that it appends to the communication. It uses things called sequence and acknowledgement numbers to track the order of the packets transmitted and received and look for ones that are missing. We'll talk about that in more detail later, but all you need to know is that it's an additional chunk of data that is then added to the packet. So in this case, you see it's added in front of the HTTP data, essentially encapsulating it. So the HTTP data is encapsulated by the TCP data, and that's what we have shown here. Now, next we have to be concerned about getting our packet out of the network. Google, I don't work for Google, so Google's web server is not in my network, and even if I did work for Google, it's probably on a different network within their organization. So this packet's going to have network-based addressing. It's going to have an IP address in most cases to be able to communicate out on the internet and be able to be routed appropriately. We're talking about routing between networks here. So again, the IP data, which is going to include a source and destination IP address, among some other things, is added to this collection of data. So whereas we once had HTTP, we now have HTTP, which is encapsulated by TCP, which is encapsulated by IP, and we have these three segments of data together. Now, in order to begin this process of routing my packet to where it needs to go, I actually have to get my packet to a router on my network. So I have to actually do some communication within my own networks to forward that data along. And that's going to be done at the data link layer, in this case with Ethernet. We're talking about a MAC address, a physical address that allows me to communicate on my own network with the router. So we're taking this addressing information, which is going to include a source and destination MAC address, and we're again appending that to this collection of data. So we now have HTTP data, TCP data, IP data, and Ethernet data. And that's actually going to complete our packet. That whole process we just went through was the process of building this packet. And it's a process called encapsulation, where we're encapsulating different segments of data on top of each other, so to speak, so that when that packet, first of all, that packet has everything it needs to get to the destination system. And when it does, so that destination system can process it in the correct order. And that's what you see happening there on the physical layer. We'll assume that this goes over a physical cable. It's routed to all the devices it needs to be routed to, and they're of course reading the information they need. So they're reading things like IP information or Ethernet information, things of that nature, to get this to this destination host on the right side of the screen. Now, when we get to that host, we're going to go through the exact same process, but in reverse. And this process is called decapsulation. So encapsulation on the left, decapsulation on the right. And that's to say that the data link layer on that system is first going to read off the Ethernet data, and it's going to be stripped. And not actually stripped, but for the most part, it's just going to be read, and then the packet is going to be passed up the chain, at least the data that's necessary, and any additional data that's not necessary will not be read. So when we get to the network stack on the system, the IP address is going to be read. This is where the system is making sure that it's receiving data that's actually intended for it, and not other data that was sent erroneously to it. From there, the transport layer is going to be processed. So we're looking at those sequence and acknowledgement numbers that determine the order in which packets should be in to make sure that there are no errors, that we're not missing a packet amongst a sequence of packets. And then from there, the application layer data is all that's left, and that HTTP request is passed up to the web server, which is going to know how to process that data. So if my system said, I'm going to do an HTTP GET request for index.html, on the right side of the screen, the web server would receive that request, and then it would be able to process it by fetching index.html and formulating that into a packet or several packets that contain the data, and then sending it back in the exact opposite direction. So in this case, adding a TCP header, adding an IP header, adding an Ethernet header, and then sending it back one or probably multiple packets going the other direction. So this is ultimately this process of building and reading packets. And hopefully that made sense. We'll go through one more example here in a second. But really, this is the process that happens for every single packet that's sent and received on a system. Again, we think of things in terms of chunks of data. An HTTP request may be only an individual packet, and often is. So we're requesting that index.html. So we see one request packet. On the flip side, sending that data back is going to be a lot bigger. We can only have packets that are up to a certain size. So we're probably going to send those in multiple packets. And for every single one of those data packets, even though it's responding to a single request, we're going to follow the same process of encapsulating the data and decapsulating it. So this is a very important concept, and it's really important for showing how protocols work together to build packets that we're using for network communication. It's also why we use terminology relating protocols together in terms of protocols riding upon one another. So for instance, I know that HTTP always relies on TCP and IP to perform its activities. So I would always say that HTTP rides on TCP. It relies upon it because it always gets encapsulated with it to do this job. Other protocols would rely or ride upon different protocols. So the example we're about to look at, we'll look at DNS. DNS does not ride upon TCP. It rides on UDP. It doesn't utilize the features that TCP has to offer. So you'll hear me throughout the course use the concept that HTTP rides on TCP or so on, that these protocols ride upon each other. And that's really to demonstrate the relationship between the different protocols at the different layers. While HTTP in itself is a powerful protocol, we cannot rely on HTTP alone to get data from one network device to another. It's this interplay of protocols which allows us to build these packets, these little self-contained units that are capable of traversing multiple systems, multiple routers to get to a location and perform some type of function and relate and work with the host operating system. Let's look through one more example of encapsulation and decapsulation here using a few different protocols. This is ultimately the same diagram, but we've replaced a couple different protocols because we're now representing a DNS transaction. So when we talk about DNS, we're talking about the domain name system, which is what allows us to resolve host names like google.com to IP addresses like 74.224.221.12. The idea being that the names like google.com are easier to remember, and that's important for us for navigating the web. In the last example, we looked at HTTP, and oftentimes before an HTTP transaction occurs, a DNS request and response have to occur in order to find out what the mapping of domain name to IP address is. So we'll go in depth on DNS later. But for now, just understand this is another protocol doing some specific function of getting data to another system and getting a response back. In this case, we have this concept of a request and reply. So you see the request being formed on the left and being received on the right. In this case, we start again with the application layer where a DNS client, in this case one built into the operating system most likely, is requesting a specific mapping. So it's going to say, hey, google.com, what IP address is associated with your with google.com right now, or maybe more specifically www.google.com, that subdomain. Not clear here, but one of those types of things. So in this case, we have DNS, and as I mentioned previously, DNS does not rely on TCP at the transport layer. It has its own built-in needs or built-in functions for a little bit of reliability, but mostly DNS is concerned about speed more than anything. And so it relies on UDP instead of TCP for transport layer activities. And UDP really means that, transport layer is responsible for reliable data delivery, and I'm going to do some very simple checksumming. But other than that, there's not going to be any sequence or acknowledgments numbers. You're kind of on your own or have to handle that somewhere else. So UDP a lot more streamlined, a lot faster in that regard. So DNS relies on UDP, it rides upon it, and we see that data being appended at the transport layer. Now, although UDP is different than TCP, they both rely or can rely upon IP to perform their function. In this case, we see at the network layer, IP data is appended, and at the data link layer, Ethernet data is appended, just like in the previous example. Once that packet is built, it is transmitted over a physical medium, probably traversing a couple different routers and things to get to a DNS server. Now, this could be a local DNS server, so it could be one on the same network segment. We'll assume it's one on a different network segment. At that point, the decapsulation process begins, and Ethernet data is read by the data link layer processes. IP data is read by network layer, UDP data is read by the transport layer, and finally the DNS request is received by the DNS server where it can be processed. The idea being that it would get this request, what is the IP address associated with google.com, and it would respond saying, this or these are the IP addresses associated with google.com, and it would formulate a new packet in a response. Could constitute one packet, could be across many, but then this process would happen in reverse. So really, again, the same thing as the HTTP and TCP based example we just looked at, but what I wanted to show here is that you can sub in different protocols. So instead of HTTP, we have DNS, and DNS relies upon UDP, so we have UDP instead of TCP. So this kind of model, for the most part, is going to work for any type of communication you're going to deal with, and it's important for understanding kind of the fundamental makeup of packets. Now, this exact diagram won't appear in the tools you're using, but hopefully it provides a mental model for you to understand what you're seeing. Most of the packet analysis tools we're using will provide some way to distinguish what these different layers are, but essentially I want you mapping it back to this kind of representation, because this is what we're going to be working with in terms of conceptualizing the different exercises we're going to look through. And this is really the fundamental building block of understanding the interplay between protocols. If you'll remember back to the beginning of this lecture, I showed a picture or an output of text that said this was a packet when we talked about what a packet is. But of course, it didn't make a lot of sense. It was just a bunch of random digits, and certainly that didn't make a lot of sense just to the naked eye, especially if you've never done packet analysis before. So this is actually that exact same packet, but we've divided it up a little bit differently. Given what you now know about protocols and about layers, different layers of the OSI model, we've divided this packet up by the different layers. And this is actually relevant to the example we just talked about in terms of a DNS packet, because that's actually what we're looking at here. And we'll talk about how you can determine it's a DNS packet and things like that in the coming lectures. But the important thing to know is this is a DNS packet, so we have all these protocols we talked about. Particularly, we have DNS data, UDP data, IP data, and Ethernet data, and they're all right here for us in a specific order. So you'll see, starting with the lower layers, we'll start with the lower layers and work our way up, because that's how this data would be interpreted by the receiving system. We start with the Ethernet header, which is the blue section, the first several bytes, followed by black text, which represents the IP header, followed by orange text, which is the UDP header, and then finally we have the application layer DNS data represented by this greenish gray color here. So just based upon knowing how protocols interact with each other and knowing about this layered system, this layered approach of encapsulation and decapsulation, you can already start to conceptualize how a bunch of what looks to be junk data can actually be broken down and interpreted both by the system responsible for receiving it, as well as you, the human, who are responsible ultimately for analyzing it. So we can't really be expected to interpret packet data in this raw, either binary or hexadecimal format. That's not a skill that really most people are going to have. And quite honestly, if there is someone who has that skill, I probably don't want to meet them. So, so how do we navigate packets? How do we break that down into something that's more understandable and get that into a format that's more easily readable, so we can actually perform troubleshooting in a reasonable manner? The answer to that question really lies in the same concept, this concept of protocols, because ultimately, as I mentioned, protocols define the format of the data that will be transmitted between devices. And if that format is defined in a document somewhere, then ultimately programs can be made that interpret that not for machine understanding, but also for human understanding. And that's where packet sniffers are going to come in. And we're using things in this case like what we have on the screen here. This is actually a packet map, and it's a packet map or packet diagram of the IPv4 header. And in this case, this shows you the format of that header. And I've already mentioned that IP is responsible for network addressing. And you can see things there like source IP address and destination IP address, as well as some other things. You can see an identification number, time to lives. You can see protocols. So not only do we have the information we need here, we also actually have information that helps us navigate what the expected length of this packet should be. So you see IP header length there near the top left, which tells us how long this entire header should be. And you have the protocol field there at byte offset 9, which tells us actually what the next expected protocol should be. So these are all designed to be interpreted by machines for their own interpretation, but we can also run this through special types of applications called packet analyzers or packet sniffers, which will interpret this data for human consumption. So we can actually process it in the same way. Using this information, we can take a random stream of data and get from just a bunch of hexadecimal characters to a breakdown like this, where in this case we have those hexadecimal characters, but we can actually see where the fields exist here. So this is an example of a packet, and we have our IPv4 header, and we have a TCP header here, and we can see our source IP and destination IP, albeit in hexadecimal format. We'd want to convert that over, but again, we can identify where the fields exist. And if we can identify where the fields exist, we can find applications that do the same thing, but maybe do it in a little bit more intuitive manner. In this case, this is a TCP dump output of a packet, and you see that not only does it have all the hexadecimal packets at the bottom, but it also has a lot of interpreted information for us. So we see a couple MAC addresses there, we see some protocols listed, some lengths, we see IP addresses and ports. These are all things we need to be able to interpret in order to understand packets, and packet maps and understanding of protocols get us here. And not only do they get us here, they also eventually get us here. And this is a Wireshark output that's going to show a much more easily understandable output of a packet capture. In this case, we see a TCP protocol here. We see hypertext transfer protocol. We see a GET request for a web page. It looks like it's a GET request for appliednsm.com. And we're able to interpret this fully as a human, even though this is only really meant to be interpreted by machines through the use of a packet sniffer. So this is really meant to be your kind of introduction to understanding protocols and the OSI model, so you can really start to think about how we conceptually break these things down, and conceptually how a packet sniffer works and how it presents the data it does to you, and how you can interpret and use that for your own purposes. So that's going to bring us to the end of this lecture. Hopefully it does provide some good baseline information for us to start with. And certainly if you don't fully understand all the information here, make sure you go back and review and try to pull in some additional resources as necessary, because it really is important to understand this concept of encapsulation and decapsulation and protocols as well as we go through moving forward. So let's summarize everything we've gone over in this introductory lecture. First of all, packet analysis is a really critical skill for people of all sorts of professions. Whether you're a network engineer, a sysadmin, a programmer, or a security analyst, there's probably a use for packet analysis, and it's really a critical, important skill amongst all those that you're going to want to have in your tool bag to progress your career, and also to help ensure your network and the business you're responsible for helping operate or helping protect is able to do everything to their fullest of the ability in a cost-effective manner. So by joining this class and taking this course, you've already taken your first step towards developing or enhancing those skills. Next, computers communicate based on protocols that serve as a defined set of rules. Just like a spoken language, computers also have protocols with specific rules that they're required to use in order to communicate in a platform and application independent manner. To talk about these protocols and how they work together, we reference the OSI model, which is a reference model that's really used to conceptualize these concepts that we'll continually reference as we go forward in this course. Finally, packets are the result of data that's encapsulated at multiple layers to support communication. Systems that want to communicate on the network are responsible for building packets, transmitting them across the network, and then ultimately receiving a response to those, also in the form of a packet that they then decapsulate in a similar manner to the sent communication. So overall, this again is really the fundamental introductory lesson to the things we're going to continue to talk about. So make sure you understand the concepts here. Definitely feel free to extend this by going and looking at a few different protocols, looking at a few different protocol specifications, or even just the Wikipedia pages for protocols to understand a little bit about the functions they provide. Because ultimately, everything we'll be doing is based upon protocols, and we'll do a deep dive on those later. But first, we're going to talk about the different tools you would use to interpret packets. So we have tools that we can use to actually examine what protocols look like when interpreted for humans, as we discussed and as we illustrated by going through a packet that was shown both in raw hexadecimal as TCP dump output and as Wireshark output. So all that said, I hope this first lecture has gotten you really excited about diving into packet analysis. I'm looking forward to continuing on, and there's a lot more to get to.